So I want to move away from the perfect score. The perfect score is when you know P0. So when you know P0, you are really playing an amusing game, for maybe amusing for some of you or for me, which is a game for theorists. I mean, you have already know the P0. You assume you can sample from P0, and you sample from P0 using generative diffusion. That's why not? But then I want to go to something which will be the empirical score. And I want to discuss collapse. So what is that? That's the case in which I have I know only a database, and so I define my empirical probability distribution, which is 1 over n, sum over mu, equal to n, times the delta function in d dimension of a minus a mu. So a mu is my set of images of celebrities, let's say. And they live in d dimension, whatever is the representation I have adopted. And each image is a point, and that's my distribution. Okay? So that is the other extreme in some sense. It's an extreme in which I don't know what is P0, and I will work with the score that is generated from that. Okay? But of course, the immediate problem that you see, okay, how is it done, the score? So you can look at PT, empirical, of x, and this is just 1 over n, sum over mu, times a Gaussian, centered in a mu e to the minus t, and of width delta t. Okay. So you have to imagine that you have points. These are your data points. These are your celebrities. They are here, delta functions. That's at time 0. And then you start to evolve. Maybe that is the origin. So you evolve. You go towards the origin. That's the a mu e to the minus t. So at a slightly different time, you are here. And then you have a Gaussian cluster. You are here, and you have a Gaussian cluster. Okay. And at a later time, you go closer to the origin, and you broaden the cluster. So at a later time, you are here, here, here. Okay. And at a very late time, you just have a big origin. Around the origin, you have a big noise, a big e to the minus x squared over 2. Okay. And what is the ideal empirical score? The ideal empirical score is the gradient of the log of this guy. Okay. So how is it done? It is equal to minus x over delta t. That comes from the derivative with respect to the gradient with respect to x of the x squared will give me a minus x over delta t. And then the rest, I can write it like that. It is sum over mu of a mu e to the minus t e to the minus x minus a mu e to the minus t squared over 2 delta t over sum over mu e to the minus x minus a mu e to the minus t squared over 2 delta t. Here you can recognize the 2D formula. This is the expectation value of A with a measure which is a product of my initial measure, which was superpositional delta, convoluted with the Gaussian. Okay, that's a conditional measure on A given X. Okay. So that is, in some sense, the optimal score that you can get by looking at empirical data. You cannot do better than that. Okay, if you don't know the P0, the true P0, but you have only the database. Maybe it's not even defined, the true P0. So one should use that, and one could use that. One can use that. It has an advantage that it is, you don't need to train. You don't need to, I told you, you will use a score function which is parameterized by a deep network, a UNet. You put 100 million parameters there, burn a few GPU for a few days, etc., and you train it and you get something. Here you don't need a training. You can do that. You have a point x, you look at the distance to each of the a mu, and you do this superposition. So you don't need to train it. One drawback is that if you have very large database, if you want to do it, it will take time at the execution time. Okay. It's not a big problem for me if I want to understand the things, etc., because it's still a manageable time, much easier than training the big unit. But for the companies who use that in order to generate language and answer the millions of stupid questions that they receive every day, they want to do it fast and cheap. So maybe it's not the best thing for them. But there is another very fundamental reason why you don't want to do that. And the fundamental reason is that if you do that perfectly and you have done a very small delta t, etc., and you have really controlled all the approximation that you need to control, if you do that, then what you will do is that when you go back, well, you go back to the initial P0. So at the end of the backward flow, at the end of the generative process, you will get back to something which is sampled according to that. So you will generate an image which is one in your database. And that is called collapse. So collapse is avoided in practice by the fact that you don't use this score, but you use a parameterized function for this score, and you optimize the parameters, as I told you 2 days ago. And so your parameterized function, even if it is defined in terms of many, many parameters, but it is in a very large dimensional space, it is much less agitated than that. It's smoother, actually. So it will do some interpolation. And because it does some interpolation, it will kind of approximate a P0, and it will be able to do some kind of interpolation in the space of images, for instance. So that's how you generate new images. So it all depends on this black box, which is in practice the UNet that everybody uses. How does it really regularize the score? What does it do? So that is a very interesting question. It's the one that many people work on. I will not touch it. So in some sense, my talk it will not address the question of the main question of generative diffusion. In some sense, but I want to tell you what happens. So I told you what happens if you have the perfect score. You know the P0 and you use the perfect score. That's what we did. We saw the speciation. Now I want to tell you what happens if you use the perfect empirical score. And I want to study this collapse transition. And I want to understand how it happens. Well, the collapse, in some sense, is something that you can look at from this drawing here. I mean, you remember that the probability distribution in the forward process and in the backward process, they will be the same by definition. We haven't done everything like that. So it means that really, if I look at the time, which is the time of the white blobs, which are here, I look at this time, I have well-separated Gaussians. Okay. And so what will happen is that if I take a generic X, maybe that X has started from here, it will be in this cluster there. And the only Gaussian that will matter here, it will be dominated by the Gaussian from which is of the index where it started from. Okay. So it means that when I am in this situation, I am already committed, and the backward flow will take me back to this pattern mu1, which is here. Instead, when the time is long enough, if I start from a time which is in the blue region, which is here, then I have a lot of mixture of all these clusters. Basically, the Gaussians which are here are strongly mixed. And so when I run backward, even if I generated my point from mu1, maybe it arrives here, but here maybe it will go back there. Okay. So you see that there will be a time characteristic in which the backward flow will be committed to one of the data points, one index mu. It's the same idea that I had with the clusters before, but now I implement them in the data. So in fact, you can look at it as U-turn or cloning. Let me say that I define it for U-turn, but for cloning it would be the same. Imagine that you start from x equal a mu equal 1, a or a certain index mu1. You evolve it to a certain xt, and you do the U-turn from t. T is t cloning, t U-turn. You do the U-turn, you evolve it backwards. Then two things could happen. You know that backward you will flow to this distribution, so you will flow to one of the data points. And so it may happen that either you flow back to a mu1, or you flow back to another point. Okay. And you can experimentally you can measure that. You can look at the time. You can look at the probability that you flow back to mu1 as function of the U-turn time. Okay. And of course, if the U-turn time is very, very small, you have barely evolved from mu1, you get back to it. But if it is large, you get back to somebody else. So you look. We'll have a law which is like that, and this law is the time of and this law gives you the time of collapse. Sorry, what is it? What? Oh, 0, or 1 over n. Yes, sorry. Yes? Does? We will see that. That will be that's an excellent question. That's one of the things that we want to understand. So let me first, before going to a detailed computation of the collapse time, I want to give you a first idea, which is an entropy criterion. the entropy criterion will be basically it's linked to this drawing here. What I want to understand is what is the total entropy of all these blobs and how it compares to the entropy of the I mean, is it just the addition of separated entropies of Gaussian or not? It will tell me if the Gaussians are mixed or not. So let me look at the total entropy at time t, which is minus integral dx pt of x log pt of x. And I will compare it to the entropy which I call the separated entropy, which is the entropy of n well-separated Gaussians. So it is the entropy of a Gaussian mixture with n Gaussians, all these, but they are far away so that I can basically neglect the overlap between the Gaussian when I compute the entropy. And so this, because they are well separated, this is equal to n times, no, this is equal to, log n. And I will put, I will put a 1 over d, because this entropy tends to be extensive with the dimension. So I will look at it, I will put a 1 over d everywhere. So this is log n over d, which is the entropy associated with the choice of which is the Gaussian that I look at. And then I have to add the entropy of one Gaussian, which is 1/2 plus 1/2 log of 2 pi delta t. So I can write in general the entropy excess, and the entropy excess will be f of t, which is equal to the entropy of separated Gaussian minus the actual entropy that I have at time t. Okay. Oh yeah, that's the PE. Yes. And what happens if t, okay, let me look at, where can I go? If t is much larger than 1, then I have delta t that goes to 1. I have the explicit formula for the separated, but then I know that pt of x goes to e to the minus x squared over 2, and so the entropy S of t, even for the pt empirical, does not matter. The entropy is 1/2 log 2 pi plus 1/2, and then delta t goes to 1, and so the entropy excess goes to f of t goes to log n over d. Okay. And I will be particularly interested in the case in which the number of data points scales exponentially with the dimension. So this I will call it alpha. Means that I have taken n is equal to e to the alpha d. Why do I do that? Because I anticipate that my phenomenon is a problem of my whole problem of collapse. It's a problem of interpolation in large dimension. Interpolation in large dimension is something that is completely controlled by the curse of dimensionality. So in order to have a good interpolation scheme in large dimension, you should have exponential number of points. So I can expect that there will be, and I can see it immediately. The first thing that I see is that for large t, I have ft, which is like that. And then it's easy to see that when t goes to 0, delta t goes to 0, and f of t goes to 0. And so what I will have in general, I will have a curve which is f of t, maybe over alpha, which goes from 1, function of time, it goes from 1 to 0. And you can compute it explicitly in models. For instance, you can really do it fully if you take a Gaussian mixture, for instance, and you can compute explicitly this curve. But you can also measure it experimentally on database, and I will show you some data later on numerical experiments. Okay, so what you expect really is that, so this gives you, it compares, let's say, the entropy of the distribution that you have arrived at time t to the entropy of separated Gaussian blobs around each point. So when this is 0, then it means that you will have collapse. So that's a very kind of generic criterion that you can use on any kind of database. But then I want to show you a detailed computation of the collapse time. Sure.
So you say that you could use this exact empirical score, right? But you realize that if you're in this framework, you actually don't need to use any kind of diffusion model, because at any finite time, what the PET is really a KD, a kernel density estimation with a given width.
Absolutely.
And so it's very easy to sample from it, pick a data point.
Absolutely. Definitely.
So on the other hand, we know that KD don't work very well in large dimensions. So is this analysis of the collapse time in a way equivalent to trying to choose what's the width of the kernel in the KDE? Because this raises so many questions.
It is okay. So maybe I should. Okay. So let me answer this question, and then I will do the explicit computation later. So it will bring me to. I will repeat the question, and I will do my chapter 8, because chapter 8 is the answer to Eric's question. But I can do it now, and so that I will postpone the complicated computation. I will postpone it later, so that you can listen to the story. Let's say. So the story is the following: that. You're absolutely right. What the perfect empirical score does is a kernel interpolation. Is a kernel interpolation with a certain width delta t, and that's it. Okay. And the question is when it is good or when it is not good. So in fact, what we will see in some detail is that let me get back to my favorite drawing, which is what happens as function of time. I start from a data point. I have the mean, which will decay to 0, and then I have the noise, and the noise increases, etc., etc. And maybe I have a structured data with some modes, and these modes, maybe there are 2 modes, and I will have other trajectories which can do something like that. Or maybe I have another bifurcation with a second mode here, so I will have things like this. But then, if I zoom at short time, and if I use the empirical score, what will happen is that here, this is my, let's say I am in Curie Weiss. These are all the configurations which are magnetization plus m star. Now what I have is that I have sampled some of them, and I have given you n of them. So I put them here like in another space. They are all at magnetization m star. I have n of them. And so what will happen in the backward flow is that at some point, this trajectory, it will be committed to going there. And I know that if I do the U-turn, I start from here, I go there, it will go back here. So it means that all these trajectories, here they are blurred, they are etc. But here they start to specialize, and they start to commit to one of the data points. Okay, so this is bad. this is bad. It tells you that you have done a bad interpolation. In some sense, you are too much picked on the data points. Now, so there are really three regimes in what we are looking at. There is a regime one, which is pure noise. Then there is speciation, and there might be several speciation. Like here, you had a first speciation, a second speciation, etc., which depends on the structure of the data. And then, at a very short time, there appears something which you don't want, which is a collapse. Okay. That is if you look at the perfect empirical score. First of all, if I would do again my Curie-Weiss model, for instance, or Gaussian mixture, etc., with the perfect empirical score, as soon as n is much larger than 1, I will get exactly the same phenomenology that I had before. So the empirical score, it will work perfectly here. It will have the speciation transition, etc., etc. It's only when you arrive at short time that the peaks are too narrow and are centered on the data. So basically, it separates you three regimes. There is regime 1, regime 2, and regime 3. So regime 1 is noise. It's before the speciation takes place. Regime 2 is when the speciation takes place. And imagine, for instance, just for simplicity, let me focus on the case in which there are only two clusters. But you could have several speciation. It would work the same. So regime 2 is an interesting regime because it's a regime in which you have found the structure of your data, but within each cluster, you are not committed to a data point. So it means that this measure here will be a good generalization. And the regime 3 is when you collapse, and so it means that it's a bad regime. It's a regime in which you are just memorize, and you flow back to something that you have memorized. So seen from that point of view, there are two things that you have to be careful about. One thing you have to be careful about is what happens here. And here you need to have a good score. And the empirical score could be a good score. It is a good score. And then the other thing that you have to focus on is, well, you are in the generalization phase. You have already done a good part of your job. You have specialized to the image of cats, if you had cats and dogs or something. But then you still need to evolve up to time 0, because until you have time 0, you are still blurred by noise. Imagine that you were looking back at Curie-Weiss. If I am here, I have real variables. They are not plus or minus 1. They are not, they don't look like configurations of Curie-Weiss. So you need to put them back. But you remember that there was an easy way, because here I could use a score that was just factorized. It was the score on xi depends only on xi. It's just an effective action for one spin. They are decoupled. So the score becomes simpler to do. But if you use the empirical score, then you fall into the memory phase. So the whole challenge seen like that is to say, be careful, get into the generalization phase, and then in this generalization phase, you should stop using the perfect empirical score, and you should use regularized score. But at the same time, regularized score should be easier to find, because basically you need to have a score for the trajectories which are here, another one that are for here, etc., and they don't mix. You have separated regions of phase space. If you look at the score for a superposition of Gaussian, it will be a superposition of linear score centered around each of the Gaussian with the Gaussian weights, etc. It's just already a complicated function. But if you focus on one of the Gaussian, it's a linear score around that. So that's very easy to learn. Okay. So the whole idea of using a neural network for doing that will be to regularize, will be to get away from that, at least at short time. And the message that we get from all this analysis is that what matters is really when you get close to the collapse time. When you are at time much above the collapse time, you don't you don't care. You can use the kernels. It works well. There is no problem. You have a smooth distribution, and your evolution does well. But when you get here, then you have to regularize. On the other hand, things should become simpler, because you just need, for instance, if you are in an image, it's very important. If you are in an image here, you will generate the high frequencies. So you will generate an image that looks nice. If you stop the things here and you project a celebrity here, it will be all blurred. It will not. Nobody will post it on the web or whatever. So you lose. But okay. So that is the idea. Does it answer your question or not quite? Let's discuss.
I wanted to know in this last phase, I wanted to make a connection between this and really kernel density estimation, which is what is being added to it at the end, if you take it from this perspective. And also maybe as a result, trying to understand a little bit better, or to not use a noise which is isotropic, because this is kernel density estimation with something isotropic, just this delta scalar.
Okay. Well, we can discuss it. We are finishing writing a paper with Giulio exactly on that. So we are exactly that. No, that's the perfect question. That's the clear thing to discuss. And in some sense, what I will discuss now also gives a way to discuss the limit of kernel density approximation. That's exactly it. Yes?
In this picture, you define the collapse time for this imperial, but you missed it. Define the speciation, because it seems like from the speciation time we needed this collective variable, but here we didn't. We know if there.
Oh, if you are just doing an experiment, you see, I use the same U-turn or cloning, but the criterion is different. When I plot the for collapse, I plot the probability that I get back to exactly the same image. And that will tell me that it is collapsed. When I look at speciation, I imagine that I have a database of images which are well separated. We took, I don't remember, we took the cars and the horses. And so you do the forward process, you do the U-turn, and you see if t is less than the t speciation, when I start from a car, I do the U-turn, I will find back a car. So? No, the cars are not all the same. It happens that they are. It happens at the. Hey, that's a good point. It happens that the typical distance between two images of the car is smaller than the distance between cars and horses. It does not need to be like that. I mean, there are other cases in which it is not like that. But let's say in the most obvious cases, it will happen like this. Okay, so the detailed study of collapse is amusing because it relates to well-known problems of statistical physics of disordered systems, actually. And I will look at this probability distribution, and I will look at it around a point x, which has been generated. Imagine that I do the U-turn. So So I start from A1. I start from the data point A1. And I generate point x at time t. So I find x, which is A1 e to the minus t plus the square root of delta t. And this is a normal variable isotropic. And now I want to understand what is the structure of this pt of x. So this pt of x, I can write it like that. I will first take out all the trivial factor. I will write it as 1 over n square root of 2 pi delta t to the d. Okay. And then I will write it as z1 plus z from 2 to n. And I have z1 is just this Gaussian factor around A1. And z2n is sum over mu e to the minus x minus a mu e to the minus t squared over 2 delta t. So basically, in order to study, so first of all, let me insist on one thing. X minus x squared, I have vectors in dimension d. They have components which are order over 1. X squared is over the d. Okay, so typically, these exponents, they are over the d. And I am looking at what happened in the large d limit. So I will have exponential dominance. There will be some points which will be dominant over other ones. And so basically, and then the second point I want to insist on is the following. Z2 is a sum over n minus 1 terms. And I remind you that I take n is equal to e to the alpha d. So n minus 1 is like n. It's a sum of a large number of terms, an exponentially large number of terms, with factors which are of order e to the minus d. Okay. This is well known in statistical physics. And for a given x, and then the next thing is that for a given x, each of the a mu that appears here is sampled independently according to a certain probability distribution P0, which is the one that I wanted to study. So if the a mu are IID sample according to P0, then what I could do is define an energy variable, epsilon mu, which would be 1 over d x minus a mu e to the minus t squared over 2 delta t. And I will find that z2n will be the sum from mu equal 2 to e to the alpha d of e to the minus d epsilon mu. This is a sum over an exponentially large number of configurations. Each configuration has a certain energy density, epsilon mu, and the total energy, which is d epsilon mu. You look at that in the literature, it has been studied under the name of a random energy model. A model that was introduced by Bernard Derrida, I don't even remember the year, 81 maybe or something, 80. Very soon, one of the, probably the first real solvable model of a disordered system. And the thing that we will compute is the free energy of this model. So we will be interested in 1 over d log z. So let me, so the first result that happens is that when the A mu are distributed IID according to a certain probability distribution, then 1 over d log of the partition function concentrate at large d to a certain free energy phi, free energy density, free entropy density in this case. And this I have to compare it to that, to the Z1. And you see there will be two cases. Okay, so what is the typical value of Z1? Well, x is equal to A1 e to the minus t plus a Gaussian noise. So that is just e to the minus z squared over 2. So this will be like e to the minus d over 2. Okay. So I have Z1 behave like e to the minus d over 2, and z from 2 to n behaves like e to the d phi. And phi is the free entropy density of the random energy model. So there will be two cases, and these two cases it will depend on time and on the number of data points, as was asked before. And there are two cases. There is a case in which if phi is less than minus 1/2, then what you get is that this guy here is irrelevant. So this means that PTE of x is really dominated by the first terms, e to the minus x minus a1 e to the minus t squared over 2 delta t. And so it means that when I take the gradient of the log of that, I have a force that takes me back towards a1. So it means that when this happens, I am in the collapsed phase. On the other hand, the second regime is when phi is larger than minus 1/2. So now the contribution to PT of x coming from all the other, you have the sum of a Gaussian, and I have separated the one coming from A1 and all the other ones. But now all the other ones, they dominate. And so if they dominate, it means that my PT of x does not know about A1. So if I use it in the flow, it will not flow back to A1. It will flow somewhere else. So it means that I am not collapsed. So this is nice because it tells me that I now have a very good criterion for identifying the collapse. And this good criterion is when the free entropy of this auxiliary random energy model is equal to minus 1/2. Well, that's good. I can compute free entropies of REM, and so I do it, and I look at the result. Okay.
This phi is a function of t, alpha, and x, or just t alpha?
No, this phi, okay, very good. This phi is a function of t and alpha. A priori, it depends on x. You're absolutely right. But it turns out that it concentrates, that when x is generated like that, it becomes independent on x. It's the 1 over d log. It's it's really the log of the term. X is like an external quench disorder, basically. And so what you have to do is look at the free entropy for a typical x, but you know what is a typical x. Typical x is the one that has been generated this way. So the dependence on x drops.
Doesn't that mean that the score becomes irrelevant because when you take the grade of the log of the p, there is no more gradient? No, can you repeat the question?
I did not get it either.
So if this phi is what at the end will allow you to calculate p then the grad log EE is no longer there. There's no score anymore.
Okay. Well, imagine that I am dominated by Z1. It is true that Z1, to leading exponential order, it is e to the minus d over 2. But still, that is true. But still, if I look at Z1 written this way, I can compute the gradient of the log of that, and I find the score that takes me back to A1. So it happens that the Z1 itself takes the same value on all the typical points x that have been generated. So the log of Z1 concentrate, but still you can compute the gradient. I mean, it's like it's
With the C1 in the face where it seems C1 doesn't matter, are you saying that actually it still does when you calculate the score?
well, yeah, yes, absolutely. You can still compute the score, but it will take you somewhere else. And yes, absolutely. I mean, there is when you compute the score, you still need to keep the dependence on x, even if the thing has concentrated. You cannot say that it is a constant.
But maybe then to rephrase the question a little, isn't it the gradients that you should compare rather than the z?
No. No, because okay, I have erased the gradient, but you remember I had I take this, I take the gradient of log p, which is what I need. And the gradient of log p, it has a numerator which is sum over mu of a term which is x minus a mu times the Gaussian, and the denominator is the sum over mu of the Gaussians. So when one of the Gaussians dominate, I take the corresponding x minus a mu. Okay, it's a gradient of the log. So that's why I can just do the analysis this way. Maybe should I sketch the... Should I sketch... okay, maybe I just give a little... for those who have never seen the random energy model, I give a little bit of an idea how it can be done, let's say. But I will not do the formulas in detail because I don't have time. Oh, I should say something else on that, maybe also before I do the computation. This is a computation that actually, okay, Derrida was doing that in the specific case in which the epsilon are Gaussian random variable and there is no x. So he didn't have to answer these questions, which are in some sense, the hard question is related to the concentration in x. But if you just say epsilon, they are IID random variable Gaussian, that's Derrida computation. The kind of new setup which is here, it actually occurred to us, and we studied it last year in a slightly different context, slightly different, but not that different, which is the context of the dense associative memory. Dense associative memory, also called sometimes modern Hopfield networks. So they are energy-based models, and they are kind of related because well, probably everybody has heard about the Hopfield model. The Hopfield model is a model of Ising spins AI, which would be plus or minus 1, with an energy which is minus sum of Jij, AI, Aj, and you take Jij as a superposition of patterns which are specific configuration. So that is a model that is well, and mu goes from 1 to n. And if n is finite, you can see that this energy function, it has minima around each of the stored patterns. So it is a way to shape the landscape on the hypercube in such a way that you have local minima of the energy in each of the patterns that you want to store. The only, well, one of the problems of the, so it's a very important way also used for the whole neural networks, etc. But from my point of view, I will see it as a model of geometry in large dimension, in which I want to have an energy function which has minima here and there and there. And so this is nice. The problem of the Hopfield model is that as it is defined here, you have the number of objects that you can store is limited, and you find that the number of patterns you can store is must be less or equal to a critical value times d. Let's say it's 0.14 times d. So you can store in d dimension a number of objects which is relatively small. On the other hand, if you look at, instead of taking two-body interaction, you go to three-body interaction, then you find that the critical number of patterns you can store goes like d square. You go to p-spin interaction, it scales like d to the p minus 1. So this tells you, well, look, there is a way to shape the landscape in such a way that you have many attractors. You can go up to n equal p minus 1. And n to the p minus 1 if you take p-spin interaction. And then people started and Hopfield and Krotov took a step further, which is to define an energy function, which is an energy function which is really which is related exactly to that. That is, they wanted to shape the landscape in such a way that you could have an exponential number of attractors. And so basically, that is what we are doing here. Imagine that a mu would be binary configurations of spins. They would be patterns that you want to store. And then you could define an effective energy of the Hopfield model, which would be exactly all these things here. And so if you start not too far from A1, you find that you have an energy well that takes you back to A1 if you have chosen a time which is less than the collapse time. So it means that you have memorized this pattern. And so depending, of course, on the value of this t and on the noise, you can compute the phase diagram of that, and you can understand how many patterns you can memorize. So that is the capacity. And it turns out that the capacity of the modern Hopfield network is alpha c, which is now log n over d should be less than a certain value alpha c that we can compute. And so that's what we were doing last year with Carlo Lucibello. And the computation is exactly the same one as here. It's a random energy model. And X is now interpreted as you look at pattern A1 that you have memorized, you look at a certain distance given by the time, delta t, you have added noise, and you see if the measure is dominated by A1, and so it means that just a gradient flow will give you back to A1 or not. And so it's exactly the same computation. You have to know whether Z1 dominates or Z2n dominates. And so you have to know whether the free entropy of the REM is larger or smaller than -1/2. And now I have done what I wanted, which is that I don't have time to do the REM. But Okay, the REM is a very standard exercise. It has been around for more than 40 years. Still, the variant which is here is not trivial. It needs some care, especially because you have to take into account the x and take into account the fact that your distribution of these energies, it is conditioned to the value of x, and then you will have to do to see what happens for a typical x which has been generated this way. So there is a kind of self-consistency condition that you have to impose. But in any case, I know that it would take me more than half an hour to do it, so it does not make much sense. So let me not do it. You can look at that in the literature. And no, I think that basically, if I just want to take 2 minutes for a conclusion. Is there a question? No? 2 minutes for a conclusion, I would say. Okay, so we are in the case here where the REM has a continuous transition. Okay. Okay, there is one thing that I should have said, even if I don't do the computation. The REM, okay, let me explain the result without doing the computation, let's say. The REM is really defined by what is the distribution of these energies. If I know the distribution of A, given x, I can compute the distribution of these energies. Okay? The distribution of these energies, it turns out that because everything is in large dimension, etc., it satisfies a large deviation principle. And it satisfies a large deviation principle with a rate function, which I can call, I don't know, it's d to the d times whatever it is. Let me give it a name, does not matter much. A of epsilon. And so you see that if I look at this density, what I will find is I find that A of epsilon, it's typical, okay. A of epsilon will be like that. Typical rate function. It is dominated by epsilon star, which is in which the rate function is 0, and these are the dominant configuration. But then if I do large deviation, I can go away from that. So that would be the average value of this thing here. Okay. Now, if I look at this thing here, what I will find is that I need to sample from this distribution with a weight e to the minus a epsilon. But basically, the thing that I can look at is what are the number of energy levels which are at energy epsilon. And if I take 1 over d times the log, this will be alpha plus a. And so it will be a curve which is like that. It goes to alpha. Alpha is 1 over d log n. And so it has... and then, away from this band, there are no states, no energy levels. And then what I need to do is sample from that with a weight e to the minus d. And so if I look at, I have to compute integral d epsilon, e to the d a of epsilon minus epsilon, from epsilon 1 to epsilon 2. And then there are several cases that can happen. Either the saddle point here, so is dominated by the saddle point, a prime of epsilon equal to 1, dominated by this guy here. Or it may be dominated by this lower point. So that is a REM transition. We are in a case in which it is second order. And if you look, if you do the math, you find that the condensation point of the REM, which is when this happens, is a time which is exactly the collapse time of the backward diffusion. And this is no miracle. I mean, that's something that it has to be like that, because basically, when the REM condenses, it tells you exactly the moment in which you are dominated by one state, let's say. So it is the same criteria. So that is more or less what I could say about the REM. Just as a conclusion, I tell you back the drawing that I want you to keep in mind. I do backward diffusion in a structured model. I will have speciation. Maybe there will be several speciation. And at a very short time, I will have something that is not very much wanted, which is a collapse. And so I have 3 regimes. The first regime, which is before any speciation, then I have the regime in which I have a smooth flow in each valley, in each cluster, and then I have the regime of collapse. I think that this picture is something which is valid. We can test it. I mean, we look at it by studying simple models, Curie-Weiss, sums of Gaussians, etc., etc. Then we can also test them numerically, because there are criteria for that. I mean, criteria related to U-turn, to the entropy criterion that I was saying, etc. And then you can check that on real database if you want. So it's something that you can really transpose to real data. One thing that has not been very much exploited yet is how to use this picture in order to devise new families of scores that will be able to regularize this part that you need while keeping the detailed structure of what happens here. So in some sense, when you do it backward time like that, when you go from tau equals 0 to larger and larger tau, you are looking at your large dimensional landscape, starting from a very low resolution and focusing more and more. And what you see first is the appearance of the big 2 clusters, the cars and the horses. And then you will have the cars with which are blue and the one which are green and whatever. And then in the end, you will go to one of the cars that you had trained your model on. That's the collapse. But I think that having that in mind can help find new schemes of score functions that do the interpolation where you want it to be, but not necessarily elsewhere. Okay, I'll stop here.